Okay, so everybody likes projectile motion, right? Uh, I'm going to show you in this video how to make a visual 3D model of projectile motion using glowscript Vpython. So let's just get started. Here is a picture. I actually Googled in my Google Photos for a picture of a ball being thrown. This is an older picture of my son playing basketball, but look, the ball is in the air, and this is what we want to model. A basketball actually works pretty well for projectile motion. The key thing is we want only one force acting on the object, so just the gravitational force. So let's start with that. Here is a ball in the air with a gravitational force pulling straight down. The gravitational force is the product of the object's mass and the gravitational field G. So what do forces do? That's the only force. So if I have that force, that would be the net force. Forces change the momentum of an object. So the net force is going to be the change momentum divided by the change in time. This is the momentum principle. And so we would define momentum in this case as the product of mass and velocity. So we call P the momentum, the vector momentum, and here is the momentum at that particular instant. I'm calling it P1 because I'm going to have a P2 later. So if I use that momentum, P1, and I use some time interval P2 later, then I could say F net would be the change momentum P2 minus P1 divided by the time interval that force is applied, delta t. I multiply by delta t, add P1, and I get this. So this says that if I know the initial momentum P1 and the force, which I know, over some time interval delta t, then I could calculate P2, the final momentum. And here's what that would look like. So a little bit later, and this is a large time interval, but you see it was moving up. Now it's moving down, but still moving to the right. Still the same gravitational force acting on it. We call this the momentum update formula because it says something really important. If I know the force, and over some short time interval, we're going to use short time intervals, then I can take the momentum and use that to find the new momentum. And actually, this would work no matter what because I have a constant force. But even if I don't have a constant force, we could do this. And spoiler alert, the next video after this, I'm going to do projectile motion with air drag. Okay, just letting you know where I'm going so the force won't be constant in that case. What about position? So suppose I have some origin off to the side. It actually doesn't even matter where it is. I can locate the vector center of that ball with the vector r1. So it has position r1 and it has some momentum p1. I can define the average velocity as the change in position, the change in vector position divided by the change in time. And that looks like F net equals delta P over delta T. Same form, so we can do the same thing. So I can say that's R2 minus R1, right? Where that's the second position. And that's the average velocity. That is important. Divided by the change in time. And I get the following for the final position. So take the initial position R1 plus the momentum, average momentum, divided by m, which gives me the average velocity, multiply by delta t, and then that's going to be add that to the initial r1 position, and I get my new r1 position. Now here's where we need to make a little trick. So that would be the position. So that's r2, has some new momentum which I just calculated, and then I use that average momentum to find r2. But I don't want to do that. I actually want to use this formula. This is the position update formula, and you notice what's different. Instead of calculating the average momentum, which I could easily do, okay? It's just I don't have to. If I have a short time interval, if delta t is small, and this is where the magic is, if delta t is small, then the final momentum P2, which I just calculated on the previous slide, is very close to the average momentum. So I could just use the final momentum instead of the average momentum. It seems like that wouldn't work, okay? But it works. Trust me, I'm going to show you it does indeed work. I don't have to find the average. That's the key. I'm going to use the final momentum at the end of the time interval to find the new position. And it doesn't look like it'd work in this case because I have a large time interval, but I don't want to draw the balls right next to each other. So the next thing I need to do is to determine the initial conditions. So suppose I shoot this ball with some magnitude of the velocity, even though I wrote it as a vector, at some angle, because this is the way you usually see it in a problem. And I need to find the vector initial velocity. So here's my initial velocity vector, v0. I can break that into an x component, vx, and a y component Vy, they're perpendicular because of the nature of the x and y axis, so I get a right triangle. And with that right triangle, the angle between Vx and V0 is theta, so I can use my normal trig. If I take the cosine theta, I can solve for Vx as just the V0, the magnitude of the initial velocity, times the cosine of the angle theta. And since the y side is the opposite, then Vy would be V0 times the sine of theta. Putting this together, I get the following velocity vector, V0 times the cosine theta for the x component, sine theta for the y component, and 0 for the z component. So I'm using this angle bracket notation with the 3 component vectors just because that's the way we're going to do it in Python. That's the way it does it in my favorite textbook too. So. Okay, so that's how I would calculate the initial velocity. I need to have that in order to do that first change in momentum. Okay, so here's how this is going to work. Number one part is to calculate the net force. In this case, this is really easy because it doesn't even change. Every single time step I do, the net force is the same, so it doesn't matter. And in this case, G is the gravitational field vector. It has the components 0, oh, that's a dot, 0, negative 9.80 newtons per kilogram. Next thing I'm going to do is update the momentum. So I'm going to take my initial momentum or whatever I have at the beginning of the time interval and find the final momentum using this formula that I just showed. And that's the force I just calculated. Next, I'm going to, this is wrong. That should be R2 equals R1 plus P2 over M delta T. So I want to change that, but I don't want to start this over. So this is wrong. This is wrong. Okay, that should be R2 equals R1. I said update the position. So I'm sorry. Update the time, T2 equals T1 plus delta T, so that you have to do that too. Now I need to go back and do the whole thing over again. Okay, and I just keep on doing these steps over and over again until I get whatever I want, right? That's the idea of a numerical model. Now, in my model, I want to make 2 objects. I'm going to make a ground, and I'm going to make a ball. So the ground is actually a box. So how do you make a box in Python? We need to define, this is a box, okay? This is my ground as a box. There's a couple important parameters. We have the center of the box, and that's right there in the middle. And we describe that as a vector labeled by POS for position. So POS property of a box is the center of the box. And then we have the height, then we have the width and the length, and actually we have 3 coordinates for the dimensions of the box. So we define that also as a vector. So if you just do normal Python, this is not going to work. But if you use glowscript Vpython, so I'm going to use this in trinket.io. I'll put a link down below. You could do this in glowscript.org. You could install Python and load the visual module. Those will all work. So if I do this code, ground is the name of my object. It's the type of box which is built into Python. And then I have to give it a position value. So I said position vector 1, 2, 3 just for fun. I have to give it a size as a vector, which is length, width, and height. And then you can give it a color too. Now here's one of the important things about Python is that if I have an object like ground, I can actually access the attributes of that object. So I can say ground.pos is the vector 1, 2, 3. Ground.pos.y is the number, the scalar value for the y component of that. So it's 2. So here you see it prints out 2. Okay, so that's important in our model. For the other object, we're going to use a sphere. So here's a sphere. I drew that myself. It has a radius. It also has a position, which is the center of the sphere. And so here's how you'd make that in Python. You would say, I'd give it a name. I called it a ball, but you could call it a butterfly, or you could call it a banana. It doesn't really matter what you call it. And it's a type of object sphere. The sphere function is built into glowscript Vpython. It's there for you. So I give it a vector position. I give it a scalar radius. I give it a color. And then I can print the vector position of the ball. And I run this. I just want to show you. I'm going to show you in better when I get to the program. But this is the output. It is actually a 3D ball. Okay. glowscript Vpython takes care of all the visuals, the 3D stuff for you. And I also printed out the vector position just to show you that you can access those things. Okay, a couple more notes before you get right into the program. So there's my ball. I can print that out. I can give it other attributes. I can make up attributes. I can say ball.m, and I'm going to call that the mass of the ball. I need to give it a number, so I'm going to say 0.2 kilograms or 200 grams. I just did that, okay? Then I have theta. I just made up a name theta for the angle, and I want it to be 30 degrees. Well, you got to convert that to radians. There is more than one way to do that, but I just multiply it by pi and divide by 180 to convert to radians. And then I have my initial velocity vector, which I said before, but here you can see it's a vector, cosine theta, sine theta, 0. And then I can write down the momentum of the ball, ball.p. I associate p with as a property of the ball. So ball.p is just the mass, ball.m, times the velocity. Okay, so let's head over to the code and let's just code this up from scratch. A ball launched at some velocity. I'll pick the velocity when I get there, and we'll model out the whole thing. It's going to be great. I'll see you there. Okay, so this is the website, trinket.io. I'm starting from scratch. I've already logged in, but I just want to show you how to get to the glowscript part. So if I go up to my name after I've logged in, and I go to New Trinket, and you have all these options, but I want glowscript. So glowscript is Python with the Vpython module already loaded into it, sort of, okay? So if you just do Python or Python 3, it's not gonna have the sphere function built in, so I need to do glowscript. Now, there are actually two options here. I could do Python, or you could do it in terms of blocks. I don't like that, so I'm gonna do Python. Okay, so let's just get started. I'm gonna go ahead and make the ground and the ball. Okay, so I'm gonna say first make the ground. Ground is an object of box. It has a position of vector. I'm gonna give it a length of, I'm trying to think here. Let's do, it might be too big, but let's do 10 meters long. No, it's going to be 0. And then I want it to be, how thick do I want it to be? Let's say let's say 4, so let's say 0.2, negative 0.2. So I'm going to have the thickness of it 0.4 meters. So I'm actually shifting down the center 0.2 meters so that the actual top of the ground is at y equals 0. And there's really no reason I have to do that. And then my size is going to be the vector 10.4, and then how wide do I want it? Let's just do 2, and I'll make it green. Color equals color dot green. Now I'm going to save it. Projectile example video, and I'm going to run it. And yeah, I'm not done, right? But I'm still going to run it just because you never know if you have a typo in there or something. It's nice to see it run right away. And I also want to see it didn't work. What happened? Color must be a vector. Color equals color. I must have typed it wrong. Yeah, see? You see what happens? Green. There you go. There's my ground. And look, I can rotate this whole thing around with the, so it is a 3D object. And there's a whole bunch of other properties you can get, but I'm going to just leave it like that. Okay, so now let's make the ball. Oops. Okay, so now I'm going to make the ball. Ball equals sphere. Position, I'm going to put it way over on the left edge of the ground. So I'm going to say the position is vector -5. Let's put it a little bit above. Let's put it at 0.1, 0. And then I'm going to give it a radius of 0.1. So that way the bottom of the ball is on the ground. And then the color, I know in the other example I used red, but I'm going to use yellow because it just shows up a little bit better on the black background. I also like Trinket because it has these the windows right next to it. So there you go. Cool, cool. Okay, now I need to do some other things. Housekeeping stuff. Let's say I need G equals the gravitational field, 0, -9.8, 0. I need the mass of the ball, ball.m equals 0.2, already said that. I need V0. I'm going to put this as just a value. So I'm going to put V0 equals, let's say 10. And then theta equals 30. 30 times pi divided by 180. So now, and so I put it like that so I can change those two. easily. And then I can get ball.p equals ball.m times v0 times vector cosine theta sine theta 0. Okay, I think I'm good. So let's do time equals 0, dt equals 0.01. Now I need to do my loop of calculations. I need to calculate the force, I need to update the momentum, I need to update the position, I need to update time. So let's just start it like this. I'm going to say while t is less than 3 seconds. Just for fun, I'm going to change up. I'm going to start off like that for right now. Now, in this loop, when you make a loop in Python, you want to put a colon, and then everything that's indented next after that is in the loop. The first thing in that loop I need to put is this statement, rate. Rate 100 tells the computer, don't do more than 100 calculations per second. And since I have a time step of 0.01, that would make this ball look to be in real time. You can make it go too fast, you can make it go too slow, because you're in charge, right? But if that's how you change the rate of animation, that's what that is. Now the first thing I want to do is calculate fnet. I don't need to do this, but I'm going to. Ball.m times g. Okay. I said I would do that, so I did that. The next thing I would do is update the momentum. Ball.p equals ball.p plus fnet times gt. Now, notice here that g is a vector. And if I multiply that by a scalar, I actually get another vector. So fnet is a vector. Okay, it doesn't look like it because it's just words, but it is a vector, and that is cool. And the same thing with momentum, same thing with force. That's all a vector. Now I need to update the position. So instead of r, I'm using ball.pos, because ball.pos is the location of the ball. That is r. Okay. And let me go back up to line 18. As I said before, this is not an algebraic equal sign. It's a make equal to sign. That's why ball.p does not cancel with ball.p. I've said that a whole bunch of times. So this is going to be ball.pos. So that's actually R1. This on the other side is R2, right? Because that's after I've updated it. And then I'm going to add ball.p times dt divided by ball.m. That's ball.p is the final momentum, P2, divided by the mass, and that gives me the final velocity, which I use to calculate my new position. And delta t of 0.01 seconds, that should be small enough. Now I need to update time, t equals t plus dt. And I think I should be done. Okay, let's run this and see what happens. Let's save it. There could be an error. I like to be realistic, right? There could be an error, and I'm going to go with it. Okay, so run it. Was that not awesome? That was awesome. Because something happened, right? Something happened in that I ran it for 3 seconds, but the ball went right through the ground. And it actually hit the ground, so I got lucky. So the ground's not real. None of this is real. The computer has no physics in it. I have to do the physics, okay? So if I let it run for 3 seconds, it just does whatever I tell it to do. It zoomed out in order to make sure I could see both the ball and the, so there's the ball right there, the ball and the ground. So it just did whatever I wanted it to do. So I could adjust this to make this go just for 1 second and see what happens. And see, oh, it almost hit the ground. Actually, that just got lucky. Or I could change this loop. Let's do this. Let's say while I could do while ball.pos.y is greater than or equal to 0. So I can't do ball.ps, right? Because that can't be greater than a scalar. But I can do the y component of that ball's position. And so as long as that is greater than 0, which this will actually go into the ground because that's the center of the ball. So maybe I should say greater than 0.1. Now let's run it. Now I'll see it stop right there on the ground. Okay, it didn't bounce because I didn't tell it to. Let's go back up here and do something else because we're almost done actually. We're never done. Never done. Up here for the ball, I'm going to add an attribute called make trail equals true. Now I'm going to run it again. What about that? I mean, come on, this is great. Let's do some other things. Over here, I'm going to say print r final equals ball.pos meters. Print t final equals t seconds. Now I'm going to run it. So now I know how far it went. Actually, that's the final position. That's not how far it went. If I want to do, let's do dr equals, let's put up here, r0 equals ball.pos. And then I'll do the final position minus initial. And then it'll tell me how far it went. So I didn't start at x equals 0. There, that's how far it went. Okay. Let's do this. What if I want to change the angle? Let's launch it at a higher angle. Let's launch it at 70-degree angle. Cool, right? I mean, it's kind of like a work of art, too. What about this? What if I want to do the problem where I launch a ball off of a table? So what if I start the ball off at some other position, not at the ground? What if I launch it from a 1 meter high table? If I go over here, it's so easy. All I have to do is change this to 1.1 meters. See? And it went a further distance. So I don't have to calculate these quadratic equations stuff and find the range. I can get the range this way. Now, one more thing. I don't know how much more things to do. Let's change the time interval. Look at my final time of 2.1 seconds, 2.01 seconds. Change the time to 0.001. Oh, I got to change this. It will run slow. I'll change it. I can't wait that long. Now I get 2.018 seconds. So it's a little bit different time, not much. The other one was fine because it has more calculations here. It gives a better approximation to the actual thing. I could add a graph into this, but I think I'm going to hold off on the graphs. My goal here was just to give you a visual model of building projectile motion. I think this video is probably long enough as it is, but I will save this and I will include the link down below. And in the next video, I'm going to make another video where I look at a styrofoam ball that I throw. So with the styrofoam ball, you cannot ignore the air drag. And so we'll model that one. It's going to be great. And I'll see you guys later.